Lecture 35 today. Just 3 more after today, next week. And then it's finals week. When is our final? Anybody remember offhand? Tuesday. Early in the morning? Okay. All right, so that'll be about a week and a half away or so. Wow, coming quick. So topics today will include more examples of splitting fields, this time over a finite field. At least one example, maybe 2 examples we might be able to get in if we've got time. Theorems about finite fields, more about finite fields, and then review algebraic extensions, which we talked about last time. Next Monday, I'd like to spend the first half of the lecture, lecture A, sort of trying to bring all this field theory stuff together and make it coherent in our minds. I'm trying to emphasize the theorems and definitions with examples for the most part, but it'd be good to try to tie it all together, I think. And then I think the second half of lecture 36, 36B, probably I'll start introducing Galois theory, chapter 32. And again, with all this stuff, it's too much to cover, so to speak, in the short time that we have, in the depth that would be necessary to fully understand it. So we want to just do the best that we can and get the basics down, I think. Get those basics down, and I think that'll be good. Give you a good feel for what field theory is about and what it's for, and for those who might be going on to grad school, give you a good foundation in that. Oh, got to do a story first again. This is not a sports story, but it's a story actually related to that big kid who was laughing at me when he was the pitcher and I was the hitter, but I walked and got an RBI out of it. It was the same kid in this story here. So anyway, that had happened, I don't know, in 6th, 7th, 8th grade, that baseball story happened. But I was picked on a fair amount as a kid. I mean, it wasn't terrible. Okay, I survived, it was fine. But I was picked on a fair amount as a kid, especially in junior high, we called it back then. And then when I got to high school, which for me was 10th grade, I was hoping, okay, I'm not going to be bullied here, okay? Anyway, I was still very naive about things. Okay, we were assigned lockers ahead of time. So I'm like, okay, I'll go to my locker the first day of school. Got to school on the bus, lots of other people drove. Got there later than most other people. The halls were just packed, okay? I couldn't get to my locker before my first class because I had to move so slowly through the hallways. Anyway, so I'm like, okay, I'll go to my locker at the end of the day. So I go to my classes, go to my locker at the end of the day. Somebody had a lock on my locker. Okay, we had actual padlocks that we had to use. They were not in the lockers themselves. And I'm like, oh great, somebody took my locker. Anyway, I went and found a person who said they could help me. It was actually somebody we called the detention lady. And because she did supervise detention. And she's like, okay, I'll take care of it. And evidently she put a note in the locker and said, get the lock off. And so I went there the next day or two, and I went and found my locker, and it was open for me, and so I was starting to use it. A couple days later, I'm at my locker, and there's 2 girls a few lockers away, and they're whispering something, and they're like, I overhear them saying something like, oh, there's the kid who took Jenny's locker. And I went and looked at him, and I said, it's not her locker, it's my locker. It was assigned to me. Anyway, so I ignored him. About a minute later, I feel this breath on my neck. And I sort of turn around a little bit like this, and there's this big kid, okay? And again, I'm still fairly small. I think at the start of high school I weighed 120 pounds, okay? I was pretty small. He's, I don't know, close to 200. And he goes, if you don't get that lock off that locker, I'm going to bite your ear off. And I'm like, okay. So I gave in. I took it off, and I went and found another locker somewhere. Anyway, the detention lady came by, found me a week later or something. She's like, oh, how's it going with the locker? And I told her what happened. And she's like, don't let him bully you. I'm like, sure, I'm 120 pounds, he's 200 pounds. I'm not going to get on his bad side. It's okay, I found another locker. Anyway, that was the same kid who laughed at me when he was pitching. He went on to become a professional wrestler, by the way. Not on TV, but sort of like in bars or something. I don't think he was on TV. Anyway. All right, back to math here. It's football story next Monday. Here's an example of trying to find a splitting field for a polynomial over a finite field. So here we have x cubed plus x squared plus 1. That's going to be our f of x. And it's over Z2. Z2 is, of course, a field. First of all, does it have any zeros in Z2? It doesn't. f of 0 is 1. And f of 1 is 1 plus 1 plus 1, which is 1. Also not 0. So it has no zeros. It's degree 3, and Z2 is a field. So it would be, finish it for me. Starts with an I. Irreducible over Z2 by the degree 2 or 3 irreducibility test. Z2 is a field. And that would mean that this ideal, the ideal generated by this polynomial, would be maximal in this ring. I hope you've gotten to the point where you feel comfortable understanding the distinction between these things. Z2 itself is a field with 2 elements. Z2x is a ring, not a field. Random polynomials, it's got infinitely many elements, right? Polynomials can be arbitrarily high degree. That's going to have infinitely many elements. But because the coefficients are in Z2, there's a finite number of elements of each finite degree. And we've seen, therefore, that if we make this kind of factoring, we get a field. And since this cubic, well, since it's a cubic, this factoring could be represented, we've seen, as a set of cosets where we can take the representatives to be degree 1 lower than the degree of this polynomial. In this case, quadratics. Ax squared plus bx plus c plus the coset, or plus the ideal, I should say, where a, b, and c are in Z2. You've got 2 choices for A, 2 choices for B, 2 choices for C. Altogether, you're going to have 2 cubed or 8 elements in this factoring, which will be a field. Right? This is something we've seen in a lot of examples. We can ask a couple questions then about this field. Does f of x split in this field? Or you could ask another question first. Does it even have a 0, first of all, in this field? Does it split? Can you completely factor it over this field extension? And it is a field extension of the original field, by the way, because you could consider a Z2 is naturally occurring in this field as a subfield of this, where you take A and B to be 0. The 2 cosets that look like this, that's going to form a field of order 2, isomorphic to Z2. So Z2 can be naturally thought of as being a subfield of this factoring. You might say technically not a subfield, but there's a natural mapping from Z2 to this field that would take 0 to this coset and 1 to that coset, and that would definitely be isomorphic to Z2. And so therefore, because of that, you can consider this to be a field extension of Z2, as long as you allow yourself to consider that up to isomorphism. So does it have a 0? I didn't ask that question. Does it split? Can you completely factor it as a product of 3 linear factors in this case? And is it a splitting field for f over Z2? That's actually a different question about whether it splits or not, right? Because a splitting field is kind of minimal, a minimal field extension in which the polynomial splits. It's not necessarily clear that this is the smallest field extension of Z2 in which this polynomial would split. there could be something smaller, at least a priori. The answer is it will be a splitting field, but theoretically, before you investigate it, you might not know. And how can you answer these questions? Well, you can do calculations to try to answer them. One thing we saw, the first thing we should emphasize, is it definitely has a 0. F of x definitely has a 0 in E. I've mentioned this before. This is essentially the proof of that fundamental theorem of field theory, Kroneker's theorem. X plus the coset is a 0 of f of x. It's kind of strange, but this is one way to think about it. Plug in x plus the coset, f of x, into f. Kind of a strange thing to do, but certainly can be done, because you think about the polynomial f of x, think of it as a function. It's just defining some operations in the field, multiplication and addition, that can allow you to find an output. This is a field. We can do multiplication and addition. We can plug it into the polynomial f itself. Which means we've got to take the coset and cube it, then add the coset squared, then add 1, though this 1, if we're doing this, should be interpreted as the coset with representative 1. It should technically be interpreted as 1 plus the ideal. And then it's just coset operations. When you multiply cosets, you multiply the representatives. So if I cube this, I cube x. If I square this, I square x. Right? That's just the operations that you do in the factor ring. And then, when you add cosets, you add the representatives. So you can write this. But hey, that's f of x there. That gets sucked into the ideal, right? This is the same as the ideal itself. It's meaning it's the same as the 0 of the factor ring. This is a fundamental thing you should know. That when you do something like this, when you've got an irreducible, and you create this factor ring, it's going to be a field, and x plus the ideal is going to be a 0 of f of x in this field, which can be thought of as an extension field of the original field. Okay? Now, writing the ideal all the time gets to be a pain. And it really isn't doing much besides just sort of being a placeholder reminding us that these things are cosets. So maybe we should just go ahead and do all these calculations without the ideal in there. I'm not going to rewrite it, but we could do all the calculations without the ideal in there, and essentially that's what we do now. We think of that factor ring over there, because again here, which technically has elements that are cosets, and we can use 8 quadratic representatives, because there's 2 choices for A, B, and C, just as being the representatives without bothering to write the ideal. 0, 1, x squared, 1 plus x squared, x plus x squared, and 1 plus x squared. Think of those as being the elements where multiplication is done, you might say mod f of x, mod x cubed plus x squared plus 1, meaning treat x squared plus 1 as 0. because it is f of x, and when you write it as a coset, that is the same thing that is generating the ideal. And this kind of thing gets sucked into the ideal, giving you the 0. We can think of this as being 0. Where x cubed plus x squared plus 1 is taken to be 0, which is equivalent to x cubed being taken to be negative x squared minus 1, which, since we're doing arithmetic mod 2, is the same as x squared plus 1. Whenever we see an x cubed, if we do multiplications here, we can treat it as x squared plus 1. Which also means x to the 4th is x cubed plus x. Multiply both sides of this by x. But wait a minute, x cubed is x squared plus 1. So x to the 4th is x squared plus x plus 1. Right? Double check it. Make sure I don't make a mistake. It's easy to make mistakes here. And going from here to here, I multiply both sides by x. So say x to the 4th is x cubed plus x. Multiply those by x. Then I replace x cubed with x squared plus x, plus 1, excuse me. X squared plus 1, and wrote it like that. That's going to mean x to the 6th is, oops, I forgot x to the 5th. X to the 5th, multiply both sides of this by x, is x cubed plus x squared plus x. I'm multiplying that by x right there. But now again, replace x cubed with x squared plus 1. But then what happens with the x squareds there? What happens with these x squareds?
They become a 0?
They become a 0. They cancel. Because we're doing mod 2 arithmetic. They become 2x squared, which is 0. You can even put slashes through them if you like. They cancel. And you're left with x plus 1. And we can continue x to the 6th, x to the 7th, etc. This then allows us to multiply things. For example, we can multiply these two things. Multiply x times every term there. It gives you x plus x squared plus x cubed. Multiply x squared times every term and maybe line up like powers. X squared plus x cubed plus x to the 4th. Those cancel. These cancel. I'm left with x plus x to the 4th. 4 there. And x to the 4th is x squared plus x plus 1. And then those x's cancel, mod 2. You're left with x squared plus 1. Double check. Okay, do take the time to really be trying to follow me here and double checking because I could easily make a mistake. Look good to people? X to the 4th is down there. Okay, I'll help you keep awake too. Okay, so in this could essentially be considered to be E. Now again, it's not really, technically speaking, the same thing as this E over here, because the elements over there are technically not cosets, but the arithmetic is the same, the addition and multiplication properties. That's an honest-to-goodness field of order 8, just like this is, as long as you do arithmetic mod x squared plus x cubed plus x squared plus 1 being taken to be 0. Show it's a field. Order 8. That tells it, we know f of x has a root. Does it split though? Are there other roots? Can I factor f of x as a product of 3 linear factors with elements in here? That's not obvious. And it would take some experimentation if you're going to do it by hand. I happened to do it in some experimentation beforehand, at least yesterday, and so I'm hoping I'm remembering this correctly. Another 0. Let's let beta equal x effectively. Can I do that? Yeah, I can do that if I want. I can use a new symbol. The reason I'm using this new symbol is because I now, in thinking about f of x, want to think of x as a variable instead of as being an element of E here. So effectively, now, I'm thinking still about the same field extension, but essentially I'm thinking of all the x's as being betas. Beta is just the symbol I happen to pick. The book does sometimes in their examples. Because I'd like to plug in these things into f of x, and so it's a little confusing if you're thinking of both x as being a variable and a ring element, or a field element. I claim beta squared is another 0, meaning essentially x squared is another 0. Plug it into f of x. Now, there's no guarantee it's going to be a 0, but I experimented yesterday, and if I'm not forgetting, I think this works out. I get beta to the 6th plus beta to the 4th plus 1. Okay, again, beta does play the role of x over here, so I guess I should figure out x to the 6th. X to the 6th is going to be x squared plus x, looking there. And I guess that does it, actually. I don't have to reduce that anymore. It's already that element. Okay, again, beta is playing the role of x here, so beta to the 6th can be replaced by beta squared plus beta. Beta to the 4th is the same as x to the 4th, so it would be beta squared plus beta plus 1. And yes, everything cancels mod 2. This is 0. Mod 2. How about the third 0, if there is one in this field extension? I forgot what it is, actually. I experimented yesterday and I didn't find it, but I forgot it. So I better try to rederive it. Probably the best way to try to rederive the third 0 is to do synthetic division. Let's start with the original cubic. So with the original cubic, this thing here, if I do synthetic division, see this is the type of problem that came out of my PhD prelim that I just didn't get, okay, at first, and I had to have Eric Gossett's help to get me to get this, and he just naturally started doing synthetic division. I'm like, why are you doing synthetic division? It's like, because that's the way you solve these problems. Okay? And I was thinking too abstractly. I was thinking about all the theorems that were in my book that were similar or even more abstract than the theorems in our book. And I'm like, how can I apply these theorems? And all I had to do was synthetic division. Coefficient of x cubed is 1, coefficient of x squared is 1, coefficient of x, there is no x up there. So it's 0. Make sure you put the 0 in there. Constant term is 1. Bring that first one down, multiply, add, multiply, add, multiply, add. Wait a minute, we didn't get 0, did we? Shouldn't we get 0? Yes, we did, because beta is a root of this. Beta cubed plus beta squared is plus 1 is 0. The remainder is 0. So when I divide this by x minus beta, I'll get a quadratic with coefficients of 1, 1 plus beta, and beta plus beta squared. But I already know beta squared is also going to be a root. So I can continue this diagram, now dividing by beta squared, or x minus beta squared, to see if beta squared is a root. It should be. Bring the 1 down, multiply, add, multiply, add. Oh, did I make a mistake? Oh, yeah. Multiplied by beta squared. beta. Beta squared. And the beta squareds cancel, mod 2. I'm left with beta plus beta cubed plus beta to the 4th, which I could reduce using these facts, but I could also notice that I could factor beta out of that, right? It is beta times 1 plus beta squared plus beta cubed, and that's 0. This is 0. And what am I left with? I'm left with now those as being the coefficients of the final linear factor. Which would be x plus 1 plus beta squared, which would mean the final root would be -1 minus beta squared, but hey, we're doing mod 2 arithmetic, so the final root is 1 plus beta squared. And I could also try to confirm that by plugging into f. I won't take the time since this is already taking long enough as it is. It will be a 0. And we can find a complete factorization of f of x. F of x equals x cubed plus x squared plus 1 equals, we can write it with minus signs if we like, x minus beta times x minus beta squared times x minus 1 plus beta squared. It's probably best to initially write it with minus signs. Then, since it's mod 2 arithmetic, I can change all these minuses to pluses. If it was mod 3 arithmetic, it'd be a bit trickier. I'd have to change a -1 to a positive 2 mod 3 arithmetic. This would be the same in mod 2 as x plus beta times x plus beta squared times x plus 1 plus beta squared. And I guess I don't really need the parentheses there, but for emphasis. So the answer to the question of whether this splits or not is yes. It does split. We can completely factor it as a product of linear factors. We haven't answered the question, though, of whether it's the splitting field for f of x over z2. Could there be some subfield of E, some proper subfield in which f splits? The answer is no, there can't be. It does turn out E is the splitting field for f of x over z2. To more fully make sure of that, we should think about a little bit about this field of order 8 that we found and what are some possible subfields of it. Mathematica for this. Here's how I program this stuff in Mathematica. So here's f of x. There's our cubic. ext is my symbol for extension field. I didn't want to use a capital E because that stands for the number E in Mathematica. I could use a lowercase e, but that just didn't seem right. So I called it ext, and there they are, as polynomials and x's, but again, I could replace those x's with betas. Polynomial mod will do multiplication in this field, or addition. Mod, these two things, mod 2 and mod f of x. So the 2 there will reduce the coefficients mod 2. And we'll take x squared plus x squared and give you 0, for example. When you add any element to itself, this field has characteristic 2, right? All these elements, all the non-zero elements have additive order 2. But we're also modding by f of x, the original polynomial, effectively treating it as 0 in this field extension. And this Mathematica does this correctly when you do this. It'll, for example, now with this notation, with the 4 here and the 8 here, it'll take the 4th element in this list, which is x squared, and the 8th one, which is this one, and will correctly multiply them to give you x. Oops, the 4th element is 1 plus x, excuse me. 1 plus x times x squared here should be, or 1 plus x times this should be x squared. Is that the example we did? Not quite. One plus x times that those cancel, giving you 1 plus x cubed, but then x cubed gets replaced by x squared plus 1. And the 1's cancel, leaving you with x squared. Confirming that Mathematica got the right thing. Wow, that blue is a nice one. Then if you use Mathematica's table command as well as table form to make it look nice, you can see the addition and multiplication tables here. Up here is the addition table. Notice zeros along the main diagonal. That's because all the non-zero elements have additive order 2. As a group, under addition, it's got 8 elements. 8 elements. All the non-zero elements have additive order 2. It's abelian under addition. It's got to be isomorphic to Z2 external direct product with itself twice Z2 plus Z2 plus Z2 as a group under addition. Under multiplication, well, ignore 0. Maybe I should take 0 out, but okay, it's in there. Look at the non-zero elements. They form a group under multiplication. I guess would be of order 7. They'd have to be cyclic. The non-zero elements would form a group of order 7 under multiplication. 7 is a prime. We know from group theory that such a group would have to be isomorphic to Z7, cyclic. And each non-identity element, everything but 1, would have order 7. Could we have any subfields of this besides the trivial subfields, relatively trivial? 0 is not a field, by the way, because fields have to have. Okay, yeah, it doesn't have unity. The smallest field, so to speak, is Z2, 0 and 1. But 7 is prime. The only divisors of 7 are 1 and 7. We're not going to have any non-trivial, non-proper subfields in this. Because if we did, say, for example, having order 4 or something, including 0, the non-zero elements would have, there'd be 3 of them in such a field. And they'd form a group of order 3, but 3 doesn't divide 7. You might guess there could be a subfield of order 4, but that's not the case, actually. Essentially, that's an outline of an argument you could give to say that this field is a splitting field for the polynomial. The answer to this question is also yes. Almost quiz time. We've only done 1 slide so far, but that's okay. It's worth it. We asked what the dimension of this field is a vector space over Z2. What is E isomorphic to as an additive group, and what are the units isomorphic to as a multiplicative group? I guess I did just answer that. And we also taught about subfields. Does it have any non-trivial, non-proper subfields? The answer is no. Thinking of 0, 1 as being the trivial subfield. Just 0 is a subring, but not a subfield. So the trivial subfield really is 0 and 1. All right, let's take a quiz.